Hello and welcome to the Chapter 2 summary video. This chapter is about atoms, molecules, and ions. So Dalton's atomic theory kind of began the idea of matter being comprised of atoms and it being a question of a given atom, what type of element is that an atom of? And so we began to discover things like oxygen, nitrogen, iron, copper, so that there are different elements, and each of the elements has something that makes it different. Later, we see that it's the specific proton count that really identifies the particular element, and then the electrons kind of counterbalance that positive charge. So you can imagine there being different elements, and there's something that makes those atoms different. We now know that to be basically the proton count. And then the atoms of a given element are all identical. We now know this isn't quite true all the time, that a particular element could have atoms that differ in neutron count. So we could imagine that different elements could be some mixture of different isotopes. But that fundamentally speaking, the properties of a particular atom are the same, relative, kind of irrespective of which particular neutron you're talking about. So even if you really note that some elements exist as more than one isotope, that really doesn't change the chemical properties of the atom. That one isotope really doesn't behave that much differently from the other isotope. Atoms cannot easily interconvert to each other, at least not by chemical means, so we're not able to convert oxygen into nitrogen and vice versa. But what we can do is change the types of bonds that might unite these atoms together. So maybe we can have compounds like NO, one N to one O. We can maybe have another compound that has two N's for every one O, maybe another compound that has two O's for every one N. So we can sort of vary the bonding environment of the atoms and come up with different compounds, but where the ratios of these atoms are a constant. So like N2O always has two N's for every one O, and that would be the law of constant composition. So the subatomic particles were discovered through a set of experiments. One involved putting a charge across some sort of material, and then seeing that a particle is being given off. If you wave a wand that, is a magnet, then you can deflect the particle that's being given off, kind of showing that the particle has a mass and a charge. So it's some sort of charged particle. And so by looking at the fact that the particle is deflected away from a positive charge, towards a positive charge or away from a negative charge, allowed this particle to be negatively charged. So it ended up being the negative electron that was being observed. Now, the electron being discovered in this sort of sense, what was really found was its sort of charge to mass ratio through J.J. Thomson's early experiments on this particular topic of putting a high voltage on like a gas source and seeing the stream of particles being generated. And so you can imagine having some sort of magnetic field, some sort of electric field that you can vary this stream of gas through to see if this particle is negative or positively charged. So the negative and positive plates allow you to pick up the movement of the particle so that the particle is found to be negative in charge, and the magnetic field helped establish that it was an actual particle that was carrying that charge. And so the Millikan Oil-Drop Experiment was somewhat similar in that it was trying to find a way to use a high energy source that used X-ray sources to try to create electrons. But in this case, they were trying to sort of create electrons on atoms within like an oil droplet spray. So they had like an oil spray where we were atomizing an oil, and then they were having these atoms drop down, and then the X-ray source was intersecting with these atoms, and then it was adding one or more electrons to each of those particular atoms. And then they had some sort of microscope view where you can sort of see by virtue of the type of electric charge that you apply, you can then work out how many electrons there were on each of the particles. And sort of they were able to find the multiple of charge was equal to 1.6 times 10 to the minus 19 coulombs per electron as the charge of one electron. And then they were also then able to use that charge to mass ratio from the previous slide to establish that the mass of the electron is about 9.1 times 10 to the minus 31 kilograms. You don't need to memorize these numbers, but just showing that the particle is definitely subatomic, smaller than the lightest known element, and they were able to work out the actual charge. Marie Curie furnished some radioactivity experiments. This slide actually says is giving credit to Ernest Rutherford, but it's really owed to Marie Curie, who won 2 Nobel Prizes for her work at the turn of the 20th century in the early 1900s. But what was discovered through looking at some radioactive materials is that some of the particles were found to be what we call alpha particles, or positively charged. Others were beta particles, negatively charged. These were like the electrons that we were observing in the previous experiments. And then other particles actually didn't carry a charge or a mass, and those were gamma rays. So let's actually look at the gamma ray first. So these were unaffected by the electrical plates or unaffected by magnetic field. So these are simply photons. But not just any photons, they're really high energy photons. They're really dangerous photons to deal with because they have such a large amount of energy. The alpha and the beta particles from decaying matter can be dangerous as well, but alpha particles are actually helium nuclei. So they're the helium-4 nucleus. Now you might learn why that particular nucleus is so stable and why it might sort of fall off of a decaying element, but you'll pick that up in chapter 21 in Chem 1220. Beta particles, these are basically our electrons. So you can kind of see you have a negative particle, you have some positive particles, and uncharged particles. So the atom, so the J.J. Thomson model for the atom was that the positive charge was spread throughout the atom. You can imagine there being positive sort of particles. They didn't quite know what neutrons were yet, so we didn't really know too much about the neutron at this time. But so the thought was that you have these protons and electrons within an atom, and so then if you imagine some sort of energy coming through, some sort of maybe like the helium nucleus. So imagine you take a particle that's going to come through at a high velocity. There's really not much mass centered throughout this atom to be able to deflect away that particular particle. Well, it turned out that this model actually was wrong. The model was found to be wrong by some work done by Ernest Rutherford. Now what he did was he took that alpha particle, that helium nucleus, so he took the helium nuclei particles. An interesting question is, at the time, did they know that was simply the helium nucleus? And I don't even know if they even realized what it was. They just knew that it was a relatively massive sort of ball of positive charge. And so what they were doing is shooting that at a piece of gold foil. The idea here is it's like kind of shooting a piece of tissue paper with a gun. You would kind of imagine the bullet to go straight through. But what they were finding is that a lot of the particles are actually scattered. Some are even like backscattered away from the actual foil. The reasoning here would be that it turns out that all the positive charge is grouping together within a nucleus. And so then you can sort of compare maybe the relative size you might expect for a single positive charge versus maybe the collection of a lot of protons into a nucleus in terms of a relative size. So you have a more massive nucleus, particle comes in, it can be deflected away if it strikes the nucleus. Now, a lot of the particles do go straight through because even in a thin strip of gold, there's really not that many overlapping nuclei. And so there is still the possibility that a lot of the particles are able to go straight through the actual gold foil. So what arose from this sort of experiment was actually the nuclear model for the atom, and then together with the later discovery of protons and neutrons being discovered in about 1932, we finally get the picture of protons and neutrons residing in the nucleus, and then electrons orbiting the outside, the relatively light electrons orbiting outside the nucleus. So here's our nuclear atom. Incoming alpha particles deflected if they hit a nuclei, and then if they don't hit a nuclei, then they would go straight through. And then without this relatively large nucleus, if we just imagine instead you had one of the atoms like that J.J. Thomson was suggesting, these dots would be very small, such that the probability of striking a particle dead on would be pretty low. Most of the particles should have gone straight through. So it disproved the plum pudding model and supported the nuclear model, this work of shooting the alpha particles at a thin piece of gold metal. So the nuclear model postulated by Rutherford was a very small, dense, positive center within the atom, and then the electrons orbiting outside the atom. Most of the atom can be thought of as space. We're talking about this in class, where you'd have electrons spinning around these nuclei. So you really do have a lot of negative charge, it's just not a lot of mass. So you end up with a lot of negative charge here, all these particles being negative. So if you bring another atom near this particular particle, then you have all that negative repulsion. So even though there's not much mass within the atom, there's a lot of charge density that's going to make it hard for atoms to overlap and get close together. So we're still going to see that the nuclei don't come in close contact. Our bond lengths for molecules, maybe take a little bit more of a closer look at that in chapters 8 and 9, that the atoms are still going to be pretty far apart. Looks like mostly empty space, but it's pretty important because it's the electron repelling each other in neighboring atoms that kind of keeps the nuclei from getting closer together. So the atom size is about 1 to 5 angstrom. It's about 100 to 500 picometers. An angstrom, 1 angstrom is a 10 to the minus 10 meter. So the size you could also think of as about 1 to 5 times 10 to the minus 10 meters. So pretty small in terms of the size of the atom. I like to say the atom's so small we actually make up a unit to describe how small it is. Other subatomic particles in the protons and the nucleus were later discovered. We were mentioning this. These were discovered in about 1920-ish and about 1932. And so then once you get the discovery of neutrons and then you get the idea of isotopes, then we can sort of begin to have the full picture of our modern atomic theory. So our subatomic particles are the protons and electrons, opposite charges of each other, but the same magnitude. So the positive charge in the proton, negative charge in the electron. The neutron is neutral in charge. But protons and neutrons carry a majority of the mass. If you look at the relative masses here, you're talking about an AMU for each of the proton and the neutrons, and about 5 times 10 to the minus 4 AMU for the mass of the electron. So you can see the proton and the neutron can carry a majority of the mass, hence why the proton and the neutron count, if we add these together, that's indicative of the mass of the compound, hence indicative of the mass number. Now the protons, they are characterizing the element itself. So this defines the atom. So this defines the atomic number. That is, the number of protons in the nucleus is directly related to which particular element the atom corresponds to. So when we look at a symbol for an atom, we can write the symbol with the mass number up on top and then the atomic number below. We usually don't give the atomic number in a lot of cases. I'm not really crossing out to say it's wrong, but we don't usually give it very often because it goes hand in hand with whatever the particular element is. So these two go hand in hand. So if you look at a periodic table, carbon's the sixth listed element. So it has 6 protons in its nucleus. If we were to look at nitrogen, it's nitrogen 7, but a lot of times we might just say nitrogen 14, and then you can imply this 7 by using a periodic table to look up the atomic number for that particular element. If there was a charge, we would indicate it here. If it's not indicated, of course, we would assume that the charge was neutral. So carbon with no charge should have an equal proton and electron count, so 6 electrons within a neutral carbon atom. So we look at isotopes. If we look at the different isotopes of carbon, say carbon 11, 12, 13, and 14 would be carbon having either 5, 6, 7, or 8 neutrons. So the neutral particle doesn't really change the properties very much for the atom. It turns out naturally the abundance of these is 0% for carbon 11. So really there's no carbon 11 in a natural sample. About 99% is carbon 12, about 1% is carbon 13, and less than 10 to the minus 10% is carbon 14. Now that tiny percent that is carbon 14 is actually useful. You can date decaying samples in terms of how old they are as a function of how much carbon 14 they still have left in them. That's a topic for Chem 1220 into chapter 21 later. But you may have heard of like carbon dating, and actually uses that small trace of carbon 14 as its basis. The atomic mass unit scale, the atoms are so small we actually invent a mass scale to describe how small they are. So the heaviest known elements turn out to have masses of about 4 times 10 to the minus 22 grams per single atom. That's a really low mass. And so the way the AMU scale works, like within this chapter, is just a simple conversion. So we define 1 AMU as a conversion into grams. We can always, interconvert our conversion factors. Imagine dividing both sides by 1.66054 times 10 to the minus 24. And if we do that, that will just give us the conversion for how many AMUs there are per gram. Only reason I'm pointing this out is because if you do this arithmetic, I'm going to do it on a calculator just so I can write down the exact digits I get. If I do 1 divided by 1.66054 times 10 to the minus 24, then I get 6.02214 times 10 to the 23 AMU. And now if you note that this number here, this is Avogadro's number. Now, it's no mistake that the number of AMU in a gram happens to equal also the number of particles per 1 mole. Now, the definition of Avogadro's number, we'll see this later in chapter 3. So we'll get this link a little bit later between, why the mole is related to the same number of particles per mole as the gram is per AMU within 1 gram. It's a very helpful system. For now, I will leave it as this, that if you know something is, say, 12.01 AMU per atom, then you would know that it's also 12.01 grams per mole. And we'll talk about these units more in chapter 3. The mole is just a larger quantity. It's an Avogadro's number of particles of the substance. But we get this nice sort of conversion between the AMU scale and the gram scale and the atom and the mole scale by the simple factor that a gram is an Avogadro's number of AMU and a mole is an Avogadro's number of particles. Again, we'll come back to that and go through that again in chapter 3 later. So the average atomic weight is the sum over all isotopes of the isotopic mass plus the fractional isotopes abundance. Another way of writing this would be that our average atomic weight would be equal to the sum over all of the fractions of a given isotope times the atomic weight of that given isotope, and we're just summing up over all isotopes. And now, the reason why this is important is because this is what we see listed on the periodic table. So when you look at the periodic table, you're going to get the average atomic weight for all the sort of naturally occurring isotopes for a given atom. So when you look at a particular element, you might say, okay, on Earth, what percent is carbon-12, what percent is carbon-13, what are their individual atomic weights, and then we could work out the average atomic weight you might want to list for that particular element. Okay, now the way we get the abundances and the actual masses of the isotopes is through an experiment called a mass spectrometry experiment. What you would do is put, say, a charge on chlorine, have chlorine with, say, a positive charge, and then you could sort of bend that particle with a magnetic field, kind of like we were talking about in the in J.J. Thomson's experiments. But you put a charge on an atom, and then you can sort of see where do we get signal. You get signal at chlorine-35 and chlorine-37, but nothing at 36 or 38 or 34, because it turns out those particular isotopes are not within a natural sample of chlorine. So chlorine is about 75%, and you could use your experiment to get these numbers a bit more precisely, but about 75% is chlorine-35, and the other 25% of a natural sample is chlorine-37. And so then if you look at the mass, you see it's pretty close to 35. You can get these masses more precise with this technique too, but it's about 35.0 and 37.0. So you may say, given that the isotopic abundance of the 35 is a little higher, then the average atomic weight should lie closer to 35. If you look at a periodic table, the mass for chlorine is listed as 35.453, and that'll be AMU per atom on average of chlorine. So the average atomic weight, we can get this from the periodic table. So now what might you expect a mass spectrum of chlorine Cl2 to look like? Now usually what you do is have a charge on here. That's how you're actually bending the substance in a magnetic field. Chlorine-2, the only idea here is thinking that you might have a 35 chlorine, 35 chlorine. You might have a 35 chlorine paired with a 37 chlorine. You might have a 37 chlorine paired with a 35 chlorine, or you might have two 37 chlorines paired together. Now, this is not a big deal in terms of, thinking through this analogy, but you might think, okay, which of these situations is the most likely? Well, 75% chance this is the one, 75% chance that is the other. So this seems like the most likely scenario. This seems pretty unlikely because it's the two lesser probable isotopes being next to each other. And then this doesn't seem so bad either because it's the one that's most likely paired with the other. So you might expect something that looks like this in terms of your mass spectrum. You might have a relatively high abundance at a peak of about 70 AMU. You might have a peak that's a little bit lesser intense at, say, 72 AMU, and then a lower intensity peak at the mass of about 74 AMU. So this, just the thought of what a mass spectrum might look like for a particular molecule, in this case, chlorine-2. So we're just sort of factoring for chlorine. You have the two possibilities here for the isotopes of that element. So our periodic table is systematically organized by increasing atomic number, and then also grouping elements into the vertical sort of columns of atoms that tend to share properties. The noble gases are usually a good one to start with because they share the property that they all exist in the gas phase as a stable atom. Everything else in the periodic table either exists as some sort of molecule, possibly as a gas, like O2 or N2 or H2, or they exist as some sort of liquid or solid. Most of our metals are solids, with the one exception being mercury among the metals, and then only one other element on the non-metal side is a liquid, that's bromine. So everything else is either a solid or a liquid, or a solid or a gas in the periodic table. Our gases, our non-metals, are on the more right side of the periodic table. Our metals are more on the left side of the periodic table. The alkali cations are the lithium group. They all form positive charged cations. The magnesium group all form 2+ charged cations. The halogen group, FCl, those form -1 charged ions. Oxygen's group tends to form -2 charged ions. So we get these similar behaviors. Getting these similar behaviors because oxygen and fluorine are picking up electrons to get that noble gas count of electrons of neon of 10. Likewise, sulfur and chlorine are trying to come up with argon's specific count of electrons. And things like potassium and calcium are going backwards. They're losing electrons to get that noble gas count. Metals almost exclusively form positively charged ions when they make ions, as opposed to negatively charged ions. Non-metals more predominantly make the anions. We'll see a little bit why in Chapter 7, but probably not too hard to understand that the non-metals on the right side are closer to gaining that noble gas count by gaining that electron, and then the metals are closer to losing the electrons to come up with that noble gas count. So our key groups, alkali metals, these are going to form plus charged ions, the alkaline +2 charged ions, just kind of showing some of their general trends. -2 ions for the chalcogen group, the oxygen group, -1 for the halogens, and then uncharged atoms, but also the only groups in the periodic table that exist in the gas phase as a single atom. So our ions, we see here are common ions, H+ or H-. Turns out hydrogen can kind of go either way. In terms of its charge, the metals here forming their plus or +2 charge, depending on which group they're in. Aluminum forms commonly the +3 charge. Transition metals, these form a variety of charge states. We'll talk about these later. So you can't easily predict the charge state of transition metals. It's not easy just to look at metals here and say, okay, whatever element is here would be a 1, 2, 3, 4, 5, 6, 7, just form a +7 charged cation. In fact, it probably doesn't even form that cation. So the transition metals, we have to have some other way of knowing their charge. We'll talk about a nomenclature system a little bit later. But cations form by the loss of at least one electron, and then anions form by the gain of at least one electron. So here are some common cations with a +1 charge. We have the H+ ion, lithium, sodium, potassium. Notice that it just takes the metal name followed by ion. So cesium ion is CS+, silver. Turns out that it forms only the +1 charged ion. Ammonium is one that we see in this case here for a molecular ion. So that would be the case of having 4 hydrogens bonded to a single nitrogen with an overall positive charge. We'll get into sketching things like Lewis structures into Chapter 8. But for now, it might be useful to think of these groups of ions, groups of atoms that have a charge of having some molecular bonds. That's these covalent linkages, where we still end up with a net charge overall on the ion as a result. So here's some other common cations with a +2 and +3 charge. So we have the members of the alkaline group. We also see zinc thrown in here and cadmium. The ones in bold are a little bit more common. Copper 2, we got iron 2. Notice that the charge of the ions actually in parentheses. Mercury 2, I'll come back to mercury 1 in a minute, but nickel 2+, lead 2+. So basically the bold ions here are ones you might want to take note of. Iron 3+. We're going to see a nomenclature system where we go name to formula, formula to name. We'll do a bunch of examples when we take a look at those, but let's look at mercury for a minute. This is a weird case, and really the only case we'll deal with here, of a metal forming some sort of metallic or molecular linkage. So imagine 2 mercuries bonded together, where you have an overall +2 charge. It's as if each mercury has a net charge of +1. So this is kind of like mercury 1, even though mercury 1 you would ordinarily think is just Hg+. So mercury 1 is not really the simple Hg+, it's really this kind of strange case of having 2 mercuries bonded together for a net 2+ charge. Now this is going to come up with anions as well in a moment. Where this comes up with in anions is like with oxygen can form O2 with a 2- charge. That's the peroxide ion. And this is kind of the same idea. 2 oxygens bonded together, negative charge on each of the O's, total charge of -2. So that's kind of one way we can think of these ions as having some molecular bonds that link the atoms together where we still have an overall charge in the unit as a result. So here's some common ions. The H- is hydride, F- is fluoride. Notice it's taking kind of the root name of the element with the IDE suffix. And so we got chloride, bromide, iodide, cyanide, hydroxide, oxide, peroxide, sulfide, nitride. So notice that most of the simple atomic ions are taking the root name of the element with the IDE suffix, and then the charge is just what you would look at a periodic table and sort of come up with. So that's relatively straightforward, and the only ones that are a little bit off the beaten path here are things like cyanide, hydroxide. So I want to make sure like we just memorize hydroxide is OH- ion. Anyone say IO? The O2 2- is the peroxide ion. You can even have O2 with a minus charge. That's superoxide. But so you get a couple weird cases with oxygen having these molecular type ions. But we get a very regular case of some other things, and some of these names we may recognize, like acetate ion is a CH3COO- ion. You might know acetic acid is CH3COOH, so you recognize that acetate ion underneath, or complementary to acetic acid. ClO3- is chlorate, ClO4- is perchlorate, NO3 with a minus is nitrate. We got permanganate shown, we got carbonate, chromate, dichromate, sulfate, and phosphate ion shown. Phosphate, sulfate, take note here. Note the charge and the number of oxygens within these formula. Notice that if you add an O, you're adding the per out in front. Okay, and so this is actually the case of oxygen 2-. If you add an O, keep the charge, you just add a per out in front, so peroxide. So if you look at a nomenclature system, we'll take a little bit more of a look at on the next slide, that the main idea here is if you add an O to a formula, you just basically throw a per out in front on the name. So this slide here is just talking about polyatomic ions, that we can have multiple atoms with a net charge. The best way of maybe thinking of this, if you're not sure of the actual bonds here, is just picture there being 5 atoms like NH4 that share a positive charge somewhere among their connection. Same thing with sulfate. Imagine you have SO4, overall 2- charge. We have some sort of molecular bonds that link the S and the O4s together. Now, formulas. A formula should be neutral in charge. So if we said write the formula for magnesium nitride, well, the nitride ion is N3-. The magnesium ion is Mg2+. I don't need to put any symbols in here for the name, because it turns out ionic compounds will just be the metal name followed by the anion name, or the cation name followed by the anion name. That we don't need to put trimagnesium dinitride or anything like that in there, because what's implied with magnesium is that that's Mg2+, because we know magnesium only forms the 2+ ion. Nitride's only the N3- ion because nitrogen's 3 away from the noble gas column, so it forms the N3- ion. And then in order to balance out the charge in this compound, we're going to need there to be 3 times as many magnesiums and then 2 times as many nitrides. So the formula should be Mg3N2. So I have a total of 6 pluses coming from the 3 2+ cations, and I have a total of 6- coming from the 2 3- ions. So the formula here is really what we call an empirical formula. The simplest ratio of these ions relative to each other is 3:2 for magnesium to nitrogen. Now, if you had a real compound, you'd have some sort of connection where you just have millions of these ions that are all sort of sticking together, just we were maintaining that sort of 3:2 ratio. Okay, so we're just maintaining this ratio of the ions within whatever the structure is, where we have millions upon millions of ions that might be interacting with each other. Okay, so our nomenclature system. Now here's just a brief overview of what we want to know how to name. We want to know how to name and differentiate ionic compounds from acids, from binary compounds, and some simple organic compounds like alkanes and alcohols. Now let's go through a couple simple cases right off the bat. So we got magnesium nitride from the previous page that we now know how to name. We can name acids like hydrochloric acid, but we could also name chloric acid, HClO3. So we can think of a bunch of formulas. These are going to look like ions that we know how to name, like anions here, but with H added on front. If you remember SO4 2-, we have a 2- charge, so sulfuric acid is an H2SO4 to balance out that charge. So the acids end up kind of being related in their naming to the sort of complementary anion that's the one underneath this sort of compound. So we'll pick up the naming system for acids a bit later. Binary compounds, these are molecular compounds, things like CO2, N2O4. These are going to pick up names like carbon dioxide, dinitrogen tetroxide. So we're going to pick up a simple system for naming these binary molecular compounds. These are molecular compounds with precisely 2 different elements. And then simple organic compounds like methane, ethane, propane. And then the alcohols of these, like methanol, lose an H, replaced with an OH. Ethanol, lose an H, replaced with OH. Propanol, lose an H, replaced with an OH. So very simple on what alcohols are. They're just a replacement of one of the hydrogens with an OH group on a hydrocarbon. Okay, so let's look at the oxyanion nomenclature system. I was inferring this a little bit earlier with the ClO3- example. So if we know this is chlorate, and I think we should memorize that, then adding an O means we just add per out in front. So we call that per and then chlorate. And so that if we take an O away, if you lose an O, then you change the ending to ITE. So if you go to ClO2-, we're keeping the charge the same. We're not changing the charge, just changing the oxygen counts here. Then we change the ite ending. So chlorite. And then lastly, ClO-, then this would be hypochlorite. So we just add hypo and keep that ite ending. Okay, now chlorine, bromine, iodine all do this exact same sort of trend. So like IO4- is periodate. IO3- is iodate. IO2- is iodite. And IO- is hypoiodite. Okay, now in the case of sulfur, the key thing we really need to know is just what is the ATE ending? This is the key thing that we really need to memorize, that for sulfur, it's SO4, so it's 4 oxygens with a 2- charge. For phosphorus, it's 4 but with a 3- charge. For nitrogen, it's 3 but with a minus. And for carbonate, it's 3 with a 2-. Okay, so we're just going to memorize those. That's it, you know. And so then if we memorize these and you start adding O's or taking O's away, then you can very easily predict the name. Now, it turns out that carbon, you know, might form carbonite. NO2 forms nitrite. PO3 forms or phosphate forms PO3 3-, and sulfate forms SO3 2-. Now, you really don't get SO5 2-. At least I don't think it's that common of an ion. But if you do, you would call that persulfate. This would be sulfite, phosphite, nitrite, carbonite. And you don't get too many of these where you add extras on, so those tend not to exist. And you also tend not to get the case where you've lost that second oxygen off these formulas. But if you did, you would know how to name it. Okay, so one thing here, we're not trying to predict why these formula exist the way they do. One of the things that we might want to appreciate is just that these are the ones that are most commonly found in nature for that particular element. So these are what we often call the representative, or the most commonly found oxyanion for those particular elements. We're not trying to memorize why, or we're not trying to understand why that's the case. We're just trying to say, well, those are the most representative oxyanions for those particular elements. Let's memorize their formula, so the oxygen count and the charge. And then let's know that if you add O's or take O's away, you can very systematically name the anions that sort of result from that task. Okay, so it's just a system of nomenclature that we're trying to learn here. So now we can also pick up names if you start adding H plus to an anion, but you don't fully neutralize the charge. If we neutralize the charge, if we go to H2CO3, this is an acid. An acid should have a neutral charge for our naming system. So if you see a neutral charge, you're going to name that substance for being an acid. This substance here still has a charge, so we're going to name this for still being an anion. It's the anion derived from carbonate ion. It's just carbonate ion, so CO3 2 minus, with an H plus added to the formula. So that changes it to HCO3 now with a net minus charge. And so all we do is throw the name hydrogen out in front. So we call this the hydrogen carbonate ion. Like if you had, say, H2PO4 minus, this is two H pluses added onto phosphate. So this would be dihydrogen phosphate ion. I didn't spell it right, but dihydrogen phosphate ion. If we had something like HSO3 minus, this would be hydrogen sulfite ion. So a very simple nomenclature system for naming these sort of things like HCO3 minus. Now you might look at that and you might think that, or know that that's called bicarbonate. That's a common name. We're trying to learn the more systematic name set by the IUPAC, the International Union of Pure and Applied Chemists. So here's a summary of our basic nomenclature rules. We should be able to know how to name the simple atomic ions that are negative in charge. These are just relative to the periodic table. So we can get the charge just using a periodic table. The name is just derived from the root name of the element with the IDE suffix. We should also be able to name superoxide, peroxide, just kind of have to memorize it. Hydroxides, OH minus, acetate ion. There's two ways to write the formula. This way is a bit more structural in the way it's given. It's probably a little bit more helpful, but it's just summarized in the carbon count, C2H3O 2 minus. Carbonate, carbonite, nitrate, nitrite, phosphate, phosphite, sulfate, sulfite. Now what you're really memorizing here are the things that are in the black font. So if you look at the memorizing sulfate, phosphate, nitrate, take an O away, then you very systematically come up with the names of those compounds as the ite ions. Perchlorate through hypochlorite, these do all three. So the chlorine, bromine, iodine kind of go that full gamut of forming all four of those ions. And then we can name the hydrogen oxyanions. These result from the cases where we have at least a 2 minus charge and at least one hydrogen being added on. In the case of phosphate and phosphite, you can have hydrogen phosphate and phosphite and then dihydrogen phosphate and phosphite. If you neutralize the charge, if you make that charge go to 0, then you're going to name the substance for being an acid. Okay, now here's the cations you should know how to name. The periodic table based derived elements, the alkali, alkaline, aluminum. And then the others that you should just more or less memorize. Zinc only forms the 2 plus, silver only forms the plus, ammonium, NH4 plus, hydronium. We haven't talked too much about this, but this is kind of like H plus, but in water. We'll pick up a little bit more about that in chapter 4. And then mercury 2, 2 plus is mercury 1. We pick up some stuff with this molecule or with this ion in chapter 4 as well. Okay, now our acid nomenclature system, pretty basic if you know how to name some of these things. You may look at HCl. I hope we all know that that's hydrochloric acid. The hydro and then the ic acid imply the IDE ending for the anion. So HBr, that's bromide ion with H plus added to it, is hydrobromic acid. HI would be hydroiodic acid. At the ending of the anion is, say, ATE. Let's do these first. So we're looking at this thing. Okay, that looks like chlorate. That looks like perchlorate. Then this would be chloric acid. And then this would be perchloric acid. So we take the 8 ending and change it to ic acid. And then for the ites, we change them to us acid. So this would be chlorus acid. And then this one would be hypochlorous acid. So you're changing the ite ending to OUS acid when you recognize the anion, sort of complementary or related to the acid. You're picturing that ion, saying what's its name, and then coming up with the name of the acid is a derivation from the anion's name. Now, the case of having these binary molecular compounds, the key there is binary is exactly 2 elements, but in any proportion, and then molecular compounds means not ionic. Now, the reason why is if you see something like TiO2, you probably want to name that titanium 4 oxide. And use the nomenclature system for name the metal cation with its charge indicated as a Roman numeral, and metal and then non-metal name. As opposed to naming it like a binary compound. So binary, we're only naming the molecular compounds with the system. We go mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca for 1 through 10 of the atoms. We just don't name mono first. So carbon monoxide, I like to point out that this is correctly named so that you can know that, okay, we're sort of seeing our rules worked out here, that no mono out in front when we have just one of the first atom. So we go di when there's 2, so dinitrogen monoxide. So see that we're choosing the IDE ending for the anion, and then carbon tetrachloride. So we name the first element first, carbon, and then tetra for 4, chloride. So carbon tetrachloride is CCl4. Now our alkanes are named as a basis of how many carbons they contain, though we have a systematic name for 1 through 4 carbons. That 1 carbon is methane, 2 is ethane, 3 is propane, butane is 4, so we have 4 carbons. Now the basic here is that each of the carbons ends up forming 4 total bonds. That's like the first 2 weeks of OChem. If you don't pick that up in the first 2 weeks of OChem, make sure to come back to understanding that carbon has 4 spots for bonds. You compare up with hydrogens for the simplest of hydrocarbons, in which case we have CH3, CH2, CH2, CH3. That's butane. And then once we have 5, then we use our systematic prefixes. So 5 would be pentane, then hexane for 6 carbons, heptane. We're using all those prefixes from the previous slide. So octane, nonane, and decane through 10 carbons. And then if you replace one of the hydrogens with a hydroxyl group or an OH group, then you just change the ending to the OL, or to OL. So methanol, ethanol, propanol. The number in front, we're not going to spend too much time talking about that, but it just indicates which of the carbons it's on the first carbon. It's not on the 3rd carbon because the 3rd carbon is really best thought of as the one further away from that functional group. And so then you could differentiate perhaps 2-propanol from 1-propanol. If you had the hydroxyl group on the middle, you would call that 2-propanol or isopropanol. So this would be 2-propanol. So you should start counting on one end and then see what number you come up with, and then maybe try counting from the other end and see what number you come up with. We get 2 in each case here. If you do that here, what you want to do is go with the number that's the lower, not the higher number, because you're basically starting counting closest to the functional group on the molecule. But we don't do this numbering system too much in general chemistry. You'll pick up more about that system in OChem. Okay, so this is just showing us the difference between 1 and 2-propanol. They're called isomers. That's probably more important to know now than anything, that these two compounds are just simply different from each other. They have slightly different physical properties, they're similar properties, but not exactly the same. So they have slightly different boiling points and melting points and, say, densities as well. Okay, finally we come to the learning objectives for Chapter 2. Let's take a glance at some of these here as we wrap up this video. After we review Chapter 2, we should be able to list the basic postulates of Dalton's atomic theory. I don't know if you should necessarily be able to list them, but I think you should understand that, the basic idea here is that matter is comprised of atoms. Atoms are of the different elements. The different elements are made to be different by, we now know their proton counts. That elements generally are the same as each other, though there might be different isotopes that they exist as that we now understand. And then lastly, we're not interconverting atoms and elements to and from each other by easy chemical means. If we have a nitrogen atom, it's staying a nitrogen atom. So if we make molecules with the different elements, we're just mixing them together in some different ratios and making bonds between those atoms. So we can describe the key experiments that led to the discovery of the electron and to the nuclear model of the atom. These are the Thomson's cathode ray tube experiment, which discovered the electron by putting a high voltage on matter and seeing a subatomic particle given off that was bent by a magnetic and electric field, suggesting a negatively charged particle. And then likewise, We had the Millikan Oil-Drop Experiment that furnished the mass and the charge of the electron by putting a varying number of electrons onto an oil droplet and then seeing how gravity and an electric field applied opposing gravity affected those droplets. The thing to take away is that the different number of electrons on the particle just changed them and their ability to be, if you will, counterposed by the electric field. So that allowed the mass and the charge of the electron to be determined, and then the radioactivity experiments helped us understand where we got a particle that we can then shoot at a thin strip of gold in the Rutherford gold foil experiment that supported and led to the nuclear model for the atom, because only a large nucleus would be capable of deflecting the alpha particles, and so that led to the nuclear model. Describe the structure of the atom in terms of protons, neutrons, electrons. So we get our proton count from the periodic table. The atomic number of the element tells us the protons within the nucleus. The number of neutrons is not something we can easily predict, but the nucleus would contain neutrons unless you're talking about a 1H nucleus which contains 0 neutrons. And then electrons as well would orbit outside the nucleus. The number of protons and electrons would be equal for a neutral atom, and they would differ for the case of ions. We'd have more electrons for anions and less electrons for cations. The relative masses of the proton and the neutron are the higher masses, relative masses of about 1 AMU each, and the electron much less massive, hence the mass number is the sum of the neutrons and the protons. We can use chemical symbols along with the atomic number and mass numbers to express the subatomic composition and isotopes, so we can say things like 13C for carbon 13. We can also write out carbon-13 for the mass number coming after the name if we want to write it out. We could also give the atomic number down here. Usually we neglect that information because you can get that from a periodic table. So that's what carbon means. It's atom number 6, hence 6 protons in the nucleus. We can calculate the atomic weight of an element from the masses of the individual atoms and a knowledge of their abundances. And I would also say vice versa, that you can take information like you get from the periodic table and solve for perhaps the abundances as well. So you can do some math here where you're just simply taking the average atomic weight to be equal to the sum of the fractional isotope times the atomic weight of the isotope, summing over all isotopes I. And then you can do and solve problems with this approach. The key is to remember that the average atomic weight is found on the periodic table. So some additional learning objectives. So we want to describe how elements are organized on the periodic table by atomic number and by similar chemical behavior. So in terms of periods and groups, so the period left to right don't agree very much in property. In fact, the left side of the periodic table you have metals, the right side of the periodic table you have nonmetals. So a pretty big change in property from left to right across the periodic table. You also then have the sort of vertical columns or the groups of elements that have similar properties from top to bottom. So like the noble gases, the halogens, the oxygen group share some of their properties together. We want to identify the location of the metals and nonmetals in the periodic table. Of course, the metals are on the left side, nonmetals on the right side. The nonmetals are close to completing their shells with electrons. We'll see that more in chapter 6. But they're trying to come up with that noble gas count of electrons. They're doing that easily by gaining electrons. These tend to form anions. And then the metals, of course, tend to form cations when they're making ionic compounds. Of course, metals can just exist as metals. They don't necessarily have to form cations, but if they do form ions, they're going to form the positively charged ones. Distinguish between molecular and ionic substances in terms of their composition. So this is maybe simply looking at something like water versus NaCl and kind of picking up the difference of nonmetallic elements tend to form molecular compounds. Metals and nonmetals tend to pair together in the forms of ionic compounds. But ICs, ionic compounds, have plus and minus ions, and then the nature is that we just have several million of these ions sort of at minimum present together. We never really have just one single NaCl unit present like we would for water. Water really is, we could look at an individual water molecule, and it might be attracted to a second water molecule, but if we had a collection of water, we'd have a bunch of different individual water molecules, where we could look at one water molecule as being something that can exist by itself. Distinguish between empirical formulas and molecular formulas. This might be comparing H2O2 versus like HO is the empirical unit, the molecular formula is really more useful for a molecule to describe its properties than, say, the empirical formula. We'll see some reasons in chapter 3 that we can experimentally determine molecular formulas, and with more data we can then find a molecular formula. So this is just more or less a foreshadow for something we'll use in chapter 3. Describe how molecular formulas and structural formulas are used to represent the compositions of molecules. So the formulas are telling us how many molecules of each element are present, or how many atoms of each element are present within a molecule for a molecular formula. If we have an ionic compound, let's say KNO3, we're being told, okay, we have 1 potassium for every 1 nitrite. So we're getting the simplest whole ratio, but of the ions relative to each other. Explain how ions are formed by the gain or loss of electrons. Use the periodic table to predict the charges. So if you have something like CaCl2, it's like saying, okay, periodic table, calcium is in the alkaline group, so it forms a +2. Chloride's in the minus group, forms minus, or it's in the halogen group, forms a -1 ion. We have to balance out the charges. Compounds should be charge neutral. And so we get a CaCl2 emerging for the formula for calcium chloride. And so then if you think about calcium, according to the periodic table, should have those 2 extra electrons. Those electrons are being lost and given over to the chloride ion to make the Cl- anion. So one of the reasons you can sort of, look at CaCl2 perhaps is to picture, okay, we have, per chlorine we have 17 electrons, 17 protons. For the calcium we have 20 electrons and 20 protons according to the periodic table. And so then if we lose 2, we go down to 18 electrons for calcium, and then we gain that in the case of 1 electron for each of the Cl- ions, and then we just do this times 2. We have 2 chloride ions. So you see it's just the Cl's taking the electron from the calcium as it gives them off. What else do we have here? We have write the empirical formula of ionic compounds given the charges of their ions. So this would be, predict the formula for something like, say, potassium nitride, K3N, because nitride is 3-, K is K+. What about the formula between, say, copper 2+, and, say, phosphate ion? So that would be like Cu3PO4 parentheses 2, because we're balancing out the 2 pluses. So we have a 6+ charge. 3- times 2 is a 6-. So balancing out the plus and the minus. The name of an IC is given in the, write the name of an IC given its chemical formula, or write the chemical formula given name. So I like to say this a lot, go name to formula, formula to name. So if we give you the formula, you should be able to name that as copper 2 phosphate. And if we give you the name, you should be able to write the formula. Or if we give you the ions and the charges, you should be able to write the formula as well. Likewise for binary inorganic compounds, I think that should say binary molecular compounds. So write the names for the binary molecular compounds and for acids. Okay. And so we talked about this before, but the acids are the case where we have H+ being added on to anions to neutralize their charge. So something like H2SO4 for sulfuric acid. So if you look at the underlying anion, you go, it's an 8. So then the acid name is something ic acid. If it's an ITE ending ion, like H2SO3, that would be sulfite ion is SO3 2-, so that would be sulfurous acid. And then if you're looking at something like HCl, that's a hydrochloric acid, hydro out in front because we're just spotting the ide ion, hydrochloric acid, so chloride to hydrochloric acid. So identify organic compounds and name simple alkanes and alcohols. The big thing here would be like, say you have the 5 carbons, so say you have pentane. So you know you have 5 carbons. So you have CH3, CH2, 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 CH3. You could count the hydrogens, I'll let you do that yourself, but it'd be a C5 compound, and you're just adding the proper number of hydrogens to make each carbon have 4 bonds. So CH3, then CH2, 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 CH3. If we replace one H with an OH group, then that's a simple alcohol, and then the name would just take whatever ending in OL. So if we make the alcohol of pentane, replace an H with an OH group, so see you have CH2, OH. On the end here, you would call that pentanol. So that's a basic introduction to, in summary of chapter 2. that's all for this video. Thanks for the attention.